All right, so deep learning, it can seem a little intimidating, right? Like this dense forest of algorithms.
Yeah.
But honestly, it's more like a whole continent waiting to be explored. And well, that's kind of what we're doing in this deep dive.
Exactly.
So we've got this excerpt. It's from a Spanish language academic text.
Oh, okay.
Deep learning, fundamentals and scientific applications. It's perfect, I think, for anyone who wants to really get a solid foundation without, getting lost in all the jargon.
Yeah, it's like a cheat sheet to understanding the core of deep learning. And the best part is by the time we're done, you'll be able to just drop these insights casually into conversations. And people are going to be like, whoa, they really know their stuff.
I love it. Okay, so the resume, or the summary, starts off with a pretty clear definition, right? It says deep learning. It's a type of AI, obviously. But what makes it so special is that it uses these things called deep neural networks. It's how they process just mountains of data.
Right.
And then find patterns that, honestly, like we as humans might completely miss.
And it's the deep part that's really crucial here. Think of it like a detective, right? They're trying to solve this super complicated case. A traditional neural network, that's like a detective with, I don't know, limited resources, right? They can maybe connect a few obvious clues.
Right.
But a deep neural network, that's like Sherlock Holmes, but like on steroids.
Okay.
With all these different layers, it can see connections that other networks totally miss, like piecing together all these random bits of information to see the whole picture.
Okay, so it's not just finding any old pattern. We're talking about uncovering these really complex relationships.
Yeah.
But this whole idea of artificial neural networks, it still sounds kind of, I don't know, abstract.
Yeah, think of it like a team of chefs in a really, really busy kitchen. Each individual neuron is like a chef with their own, like, very specific task,
Okay.
Chopping veggies, stirring sauces, grilling meat. They all work kind of independently, but they pass, like, their creations onto the next chef down the line.
Right.
And these chefs or neurons, they're all organized into layers, right? So you might have your prep cooks in one layer, then your sauciers in another.
Right.
And then finally you have the head chef who puts it all together to make the final dish.
Yeah.
So as information flows through this network, each layer kind of processes it and adds its own little touch. So it gets transformed in like increasingly complex ways.
Okay, so each layer adds a level of like sophistication.
Right.
It builds on what the previous layer has done.
Exactly.
It's kind of like a relay race, I guess.
Yeah, exactly. Like each runner gets the baton and builds on the momentum of the one before them.
That's a good analogy. Okay, I like that.
Now imagine this kitchen, right? But it suddenly has access to an unlimited supply of the freshest ingredients, like the best stuff.
Wow.
And all the most high-tech appliances you could dream of.
Okay.
That's kind of what this data explosion and these powerful hardware like GPUs and TPUs have done for deep learning. So, GPUs, those are graphics processing units, right? They were originally designed for video games, but turns out they're really good for handling these massive calculations that deep learning needs.
Okay.
And then TPUs, those are tensor processing units. They're kind of like GPUs, but even more fine-tuned for AI. So they're really the secret ingredient that allows these networks to learn from these huge data sets in a, somewhat reasonable amount of time.
So basically, we've got way more data than ever before, and now we've got the hardware to actually, like, make sense of it all.
Right.
So, like, going back to your analogy, it's like giving those chefs just a warehouse full of ingredients in this kitchen that's straight out of, I don't know, Star Trek or something.
Yeah, exactly. And now let's actually peek inside the structure of these deep neural networks.
Okay.
Because our source material, it breaks it down into these three main layers.
Yeah.
You've got your input, your hidden, and your output.
Okay, so it's like a 3-act play.
Yeah.
You've got your data entering the stage in the input layer, and then it undergoes this huge transformation in the hidden layers.
Right.
And then finally, you've got, like, the grand finale, the output layer.
Yeah.
And that's where you get your answer or your prediction.
It's a great way to visualize it. So think of that input layer like as the senses of the network. It takes in all the raw data, whether that's images, text, sounds, whatever.
Right.
Then in the hidden layers, that's where things get really interesting.
This is where the magic happens.
This is where the network does what's called nonlinear transformations on the data. It basically means it's extracting and combining features in all these crazy complex ways.
Nonlinear transformations. That sounds like something out of, like, my high school math textbook.
Yeah, it sounds complicated, but it's actually simpler than you think. Like, imagine you're trying to recognize a friend's face in a crowd.
Okay.
You're not just looking at individual features, right? Like their eyes or their nose. It's the combination of all of those features together.
Right.
The distance between their eyes, the curve of their lips,
Yeah.
all those little details that make their face unique, right? So these hidden layers, this is where the network learns to recognize those complex, nonlinear relationships, those patterns that would be super hard for us to, like, define or program ourselves.
So it's like the network's learning to see the forest for the trees.
Yeah.
Not just focusing on the little details, but the bigger picture.
Exactly. And to do this, the hidden layers use these specific functions, kind of like mathematical recipes, you could say,
Right.
to manipulate the data and highlight, like, what's really important. The text mentions ReLU and sigmoid as example.
Okay, so ReLU and sigmoid, are these like fancy kitchen gadgets that chefs use to like transform ingredients?
Perfect analogy. Let's say you're making a smoothie, right? ReLU is like that strainer that takes out all the seeds and pulp, so you're just left with this like perfectly smooth, delicious juice.
Okay.
And in a neural network, it filters out all the irrelevant, like noisy information and focuses just on the really important signals.
So it's like noise-canceling headphones for the network.
Exactly.
Okay, I like that. What about sigmoid? What's its like special culinary power?
So sigmoid, you can think of that as like the master baker, you know? Takes this lump of dough and turns it into this perfectly formed loaf of bread.
Okay.
So it basically squashes the output of a neuron between 0 and 1, which is really useful for tasks like classification.
So classification, that's like deciding if an image is a cat or a dog.
Yeah, exactly. Or if an email is spam or not.
Right.
So sigmoid helps the network assign like probabilities to different outcomes. So let's say the output for cat is like 0.9. Right. That's basically saying I'm 90% sure this is a cat.
Okay, so even though they sound really technical, these functions are basically tools that help the network make sense of the data and then like make predictions.
That's it.
It's all starting to click. But how does the network actually learn? Like, is it cramming for an exam or is it more like learning a new skill?
That's a great question. Our source material actually talks about 3 main learning styles: supervised, unsupervised, and reinforcement learning. And get this, understanding the learning style is really important for understanding, like, the application later on.
Okay, let's hear about those learning styles then.
So supervised learning, think of it like flashcards, right? Like you're trying to learn different types of fruit. You've got flashcards with pictures on one side and the names on the other.
Yeah.
You go through the cards trying to match them up, right? So in supervised learning, the network is given what we call labeled data. So that could be images of cats and dogs with their labels. And it learns to map the input, like the image, to the output, which is the label.
So it's like a matching game. The network's trying to connect the dots between the input and the right answer.
Exactly. Now imagine you have a jigsaw puzzle, but there's no picture on the box. You just got to figure out how the pieces fit together.
Okay.
That's unsupervised learning. The network has to discover patterns and structures in the data without any, like, explicit guidance.
Interesting. So it's like the network is this detective looking for clues and connections on its own.
Exactly. And then you've got reinforcement learning. Think of it like training a dog, you know, with treats.
Okay, yeah.
You give the dog a command, and if they do it right, they get a treat. If they don't, well, no treat.
Right.
So over time, the dog learns to connect certain actions with rewards and others with, well, nothing.
So it's like learning by doing, but with a system of like rewards and consequences.
Exactly. Reinforcement learning is really good for tasks that involve like decision-making and control, like playing games or controlling robots.
Wow, 3 very different ways of learning. And each one seems like suited to a totally different kind of problem. This is really interesting stuff.
It is, right.
But all this learning, all this data processing, it's got to take some serious computing power.
You're absolutely right. And actually, the source material, it specifically mentions computational requirements as like a key aspect of deep learning. Because training these complex networks, it's no joke.
Yeah, it's not something you can just do on your old laptop then, huh?
Well, I mean, you technically could, but you might be waiting a while.
Right.
Like till next year for the results.
Okay.
The demands of deep learning have really pushed the development of this specialized hardware, like those GPUs and TPUs we talked about earlier.
Right.
It's like giving those marathon runners, you know, custom-designed shoes and energy drinks.
Makes sense. So without these specialized tools, deep learning would be pretty much out of reach for most people.
That's where things get interesting. It's true that it can be very computationally expensive, but there are a lot of people working on making it more accessible.
Okay.
Like one approach is developing these more efficient models and algorithms. It's like designing a car that's just as fast, but it uses way less fuel.
So it's all about optimizing the code, making it run smoothly, and use less power.
Exactly.
Clever. What else are people doing to make deep learning more democratic?
Well, another game changer has been these frameworks like TensorFlow and PyTorch.
Okay.
You can think of them like construction kits for deep learning models. So instead of having to write every single line of code from scratch, you can use these pre-built components and tools to make your own custom architectures.
So it's like having Legos, but for deep learning.
Exactly. These frameworks are making it much more accessible so more people can experiment, innovate, and contribute to the field, which is really exciting.
That's awesome. It's an exciting time to be involved in AI, even if you don't have a supercomputer in your basement.
Exactly. Now let's look at the specific types of deep neural networks. Our source material calls them principal architectures, and each one is like a specialized tool for a particular type of task.
Okay, so we're moving from the general principles to the specific tools of the trade. I'm ready. What's first?
Well, let's start with one of the, I guess you could say, rock stars of deep learning, convolutional neural networks. CNNs for short.
CNNs, yeah, I've heard of those. What makes them so good at, image stuff?
Imagine trying to describe a painting to someone who's never seen it. You wouldn't just, list off the colors, right?
Right.
You talk about the shapes, the textures, how everything kind of relates to each other. CNNs work in a similar way. They have these mathematical filters, we call them convolutions, and they basically scan across the image, picking up on features like edges and corners, textures, you name it.
So they're like art critics, but for computers. They're analyzing the brush strokes and, I don't know, the composition.
Exactly. And because they're so good at extracting these spatial features, CNNs are really powerful for things like image recognition, object detection, even self-driving cars rely on them.
Oh, that makes sense. So when my phone unlocks using Face ID or the self-driving car spots a pedestrian, that's CNNs doing their thing.
You got it. They're like the eyes of these intelligent systems helping them see and understand the world.
That's pretty cool.
It is. But CNNs, those are just one piece of the puzzle. Now let's talk about another really interesting architecture, recurrent neural networks, or RNNs.
RNNs, okay. So what's their specialty?
RNNs, those are the wordsmiths. They excel at anything sequential, so text, time series, even audio signals. Think about reading a book. You don't just process each word individually, right?
Right.
You build an understanding by remembering what came before and kind of anticipating what's coming next.
So it's all about context, understanding how all the pieces fit together to make a story.
Exactly. And RNNs, they have this unique ability to remember previous inputs, so they can actually capture those dependencies within a sequence, which makes them really good for things like natural language processing, machine translation, even speech recognition.
So when I'm using Google Translate or talking to my virtual assistant, there's probably an RNN working in the background.
Most likely. They're kind of behind this whole language revolution that's happening in AI.
That's awesome.
Yeah, and there's a special type of RNN called long short-term memory, LSTMs. And they're especially good at handling long sequences.
LSTM. Sounds kind of sci-fi.
Yeah.
What makes them so good at, remembering things?
Think of it this way. An ordinary RNN, it's like someone trying to memorize a long list just by repeating it over and over. But as the list gets longer, it gets harder to remember everything, right?
Right.
But an LSTM, that's like someone who writes those items down on a piece of paper so they can refer back to it whenever they need to.
So they've got this built-in note-taking system.
Exactly. Pretty neat, huh?
Yeah, that's clever.
Yeah.
So what are LSTMs actually used for in the real world?
LSTMs, they're like the ultimate storytellers. They're the ones behind those predictive text features on your phone, like when it suggests the next word.
Oh, yeah.
And chatbots that can actually hold a conversation that feels almost human, even those algorithms that can generate realistic sounding speech.
Wow. It's like they're learning the nuances of language, the rhythm, the flow.
They really are.
Okay, enough about language. Let's talk about something even more mind-blowing, shall we? Transformers.
Ah, yes. Transformers. They've totally revolutionized natural language processing. Remember we talked about attention earlier?
Yeah.
That's their secret weapon.
Okay, remind me again. What was attention?
Think about reading a news article. You don't pay attention to every single word, right?
Right.
You focus on the key phrases, the sentences that have the main points. Transformers do the same thing. They can selectively focus on the most important parts and kind of ignore the rest.
So they're like speed readers, but for AI.
Exactly. And that makes them really powerful for tasks like machine translation, question answering, summarizing text.
So they're good at getting to the point.
Yeah. You've probably heard of GPT, which stands for Generative Pre-trained Transformer.
GPT, that rings a bell.
Mm-hmm.
Isn't it like those chatbots that can write poems and code and stuff?
That's it. And then there's BERT, bidirectional encoder representations from transformers. That one's really good at understanding how words relate to each other in a sentence.
Wow, these transformers are really shaking things up.
They are.
It's like they're learning to think more like us, focusing on what's actually meaningful.
Yeah, it's pretty amazing.
What other cool architectures are there?
Let's talk about something that's both fascinating and, honestly, a little bit creepy. Generative adversarial networks, or GANs.
GANs. I have a feeling this is where things get interesting.
Imagine a counterfeiter trying to make, fake money, and then you've got a detective trying to spot those. They're always trying to outsmart each other, right?
Right.
And as they do, they both get better at their jobs. That's basically how GANs work.
Okay.
You've got two networks competing, a generator network that tries to create realistic data like images or music, and a discriminator network that tries to tell the difference between the real and fake stuff.
So it's like a constant battle where the generator's trying to trick the discriminator and the discriminator's trying to catch them out.
That's a great way to put it. And as they compete, both networks get better. The generator makes better fakes, and then the discriminator gets better at spotting them. And the result is a system that can generate some really, creative and realistic stuff.
So are GANs behind those AI artists I've heard about, like the ones that are painting and making music?
Exactly. They've been used to create these incredibly realistic deepfakes, where they swap one person's face onto another in a video.
Oh, yeah.
They can even make photorealistic images of people who don't even exist.
That's both impressive and a little unsettling.
It is. It's like they're blurring the lines between what's real and what's fake.
Absolutely. Okay, any other architectures we should know about?
Let's finish up with autoencoders.
Autoencoders. Okay, what are they all about?
Think of an autoencoder like a master of disguise.
Okay.
It takes some input, like an image or text, and tries to compress it down into this tiny little representation.
So it's like a zip file for data.
Yeah, pretty much. And then it tries to reconstruct the original input from that compressed version.
So it's like a super efficient storage system.
Exactly. And that makes them good for all sorts of things, like data compression, anomaly detection, even cleaning up noisy images.
Anomaly detection. So that's like spotting those things that are out of place, that don't fit the pattern.
Exactly. Imagine you've got security cameras in a bank. An autoencoder could be trained on footage of, normal activity.
Right.
And if something unusual happens, like someone trying to break in, it would flag it as an anomaly.
Oh, that's cool. It's like a digital security guard.
Yeah, pretty much. And they're used in fraud detection, too.
How so?
Well, they can learn the patterns of normal financial transactions. So when something weird happens that deviates from that, it might be fraud.
So they're like digital detectives, always on the lookout for suspicious activity.
Exactly. Always monitoring, always looking for something that breaks the pattern.
That's amazing. We've gone from the basics of neural networks to all these incredible architectures that can see, read, create, even detect anomalies. It's mind-blowing how these algorithms are already part of our lives.
And we're really just scratching the surface of what's possible.
Seriously.
The applications are expanding so fast. It's really amazing to see how this technology is, shaping the world.
Right. Speaking of applications, I'm curious to see how all this theoretical stuff actually plays out in the real world. The source material mentions a ton of, scientific and technological applications.
Okay.
Let's dive into those.
That's where things get really exciting. Because deep learning, it's not just a theory. It's really transforming industries and our lives in huge ways. Let's start with one of the biggest areas. Computer vision.
Okay, computer vision. So how's deep learning changing things there?
Imagine a world where computers can see as well as we can, or even better.
Okay.
That's what deep learning is making possible. Take healthcare, for instance. There are now algorithms that can analyze medical images, incredibly accurately, sometimes even better than humans.
Wait, really? Are you saying computers can diagnose diseases better than doctors?
In some cases, yeah. Deep learning models have learned to detect tumors in X-rays, find signs of eye diseases in scans,
Wow.
even predict heart disease risk from EKGs. And get this, they can often do it faster and more accurately than doctors.
That's both incredible and kind of freaky at the same time.
It is, right.
It's like giving doctors a superpower.
Yeah, and it's not just about diagnosing. Deep learning's being used to personalize treatments, predict how patients will respond, even guide surgery.
So it's changing pretty much everything in healthcare.
It really is. Another area is facial recognition. Think about all those security cameras everywhere. With deep learning, they can now recognize faces, track people, even identify potential threats.
I see those in movies all the time.
And of course, self-driving cars, they use computer vision to navigate, avoid obstacles.
It's mind-blowing that cars can now see thanks to deep learning.
It really is. Now let's move on to natural language processing, or NLP. Deep learning has made huge advances here, letting machines understand and even generate human language in ways we never thought possible.
NLP, that's all about language, right?
Yeah.
So are those chatbots I see popping up everywhere a result of NLP?
That's one application, but it goes way beyond that.
Okay.
We now have algorithms that can translate languages instantly, breaking down communication barriers. They can analyze social media, figure out what people are feeling and what's trending.
Oh, wow.
And some can even write news articles, poems, marketing copy.
Wait, computers can write poetry now. That's kind of amazing.
Yeah, it's pretty wild.
But also a little scary.
It highlights just how powerful this technology is becoming. But let's move on to another exciting area. Biomedicine.
Biomedicine, that feels like an area that's ripe for disruption.
Definitely. One of the most groundbreaking things has been AlphaFold, a deep learning system that can actually predict the 3D structure of proteins super accurately.
Wow, predicting protein structures, that sounds ridiculously complex.
It is, but basically AlphaFold has learned to read those amino acid sequences that make up proteins and then predict how they fold into these intricate 3D shapes.
Okay.
This is huge because the shape of a protein determines how it works.
Right.
And understanding that shape is key to developing drugs that can target specific diseases.
So it's like having a blueprint for the building blocks of life.
It really is. It's incredible how deep learning is unlocking these secrets.
What other applications are there in biomedicine?
It's also being used to analyze genetic data, identify potential drug targets, and even personalize treatments based on a patient's unique genes.
So it's like having a personal medicine guide.
Exactly, tailoring treatments to each individual.
That's amazing. It's like deep learning is bringing about an era of precision medicine.
It really is.
Where treatments are like fine-tuned to the individual rather than this one-size-fits-all approach.
Yeah, exactly. Now, how about we take a look at the physical sciences?
Okay.
Deep learning is being used to model complex systems and make predictions about the natural world.
So like what? Weather forecasting.
Yeah, like predicting climate change, understanding weather patterns, even discovering new planets.
That's incredible. It's like deep learning is giving us a glimpse into the future of the planet and beyond.
It's pretty amazing, right? What about finance? Do you think deep learning's playing a role there too?
Oh, I'm sure it is. Probably predicting stock prices and things like that.
Absolutely. It's being used for everything from predicting stock prices to detecting fraud.
Okay.
The algorithms can analyze tons of financial data, identify patterns, and make predictions about how the market might move.
That sounds like it could be pretty lucrative.
Yeah, if it were that easy, we'd all be rich.
Right.
But seriously, while deep learning's a powerful tool for, financial forecasting, it's important to remember that markets are complex. No model can predict the future perfectly.
So it's not a crystal ball, but it can still provide valuable insights.
Exactly. It's just one tool in the financial analyst's toolbox.
Okay.
And it needs to be used with human expertise and judgment to make, good decisions.
That's a good point. We have to be realistic about the limitations of any technology, no matter how advanced it seems.
Absolutely. And speaking of limitations, deep learning, despite all its potential, does come with some challenges.
Okay, let's talk about those challenges. Our source material mentions a few limitations and challenges that are worth discussing. Let's start with the whole need for large volumes of data. Why is that such a big deal?
Deep learning models are kind of like those competitive eaters you see on TV.
Okay.
The hot dog eating contests.
Right.
They have this huge appetite for data. They need tons of it to learn effectively.
So it's not just a snack, it's a full-blown feast.
Exactly. Think about learning a new language. The more words and phrases you hear, the better you'll understand and speak the language, right?
Right.
It's the same for deep learning models. More data equals more patterns they can recognize, which means more accurate predictions.
It's all about exposure. The more data they have, the more they learn.
Exactly. The text also mentions high computational costs. We kind of touched on this earlier, but why is this such a barrier?
Yeah, I'm curious about that too. Because it seems like a catch-22, right? You need tons of computing power to train these powerful models, but not everyone has access to that kind of power.
Yeah, it's a bit of a chicken and egg problem. Training these models is like running a race car. It needs a ton of fuel and a special track.
Okay.
And in the deep learning world, that fuel is computing power.
Makes sense.
You need access to these powerful computers, specialized GPUs or TPUs, and even then, you need the knowledge to set up and maintain these systems. That's a huge barrier for a lot of people.
So it's not something you can just do on your home computer.
Not really, but luckily researchers are working on making things more accessible. They're developing more efficient models that need less power.
Okay.
And there are these cloud-based platforms that make high-performance computing available to more people.
So there are solutions in the works.
Definitely. And it's important to remember that even with these challenges, deep learning is a field that's evolving crazy fast. Researchers are always pushing the boundaries, coming up with new techniques, overcoming limitations.
So it's a really dynamic field.
It really is.
What's next for deep learning then? Where's all this heading?
That's the big question, isn't it? It's tough to say for sure given how fast things are moving. But our source material does talk about some future trends that are worth exploring.
Okay, let's dive into those. What does the future hold for this technology?
Well, one of the most promising areas is developing more efficient models. Like we talked about, the computational demands can be a real bottleneck. So researchers are trying to design models that can get the same results with less power.
Making it more sustainable and accessible.
Exactly. Another exciting area is self-supervised learning.
Right.
Right now, most models rely on supervised learning, which needs tons of labeled data.
Right, like those flashcards we talked about.
But labeling all that data, it's a huge pain. It's time-consuming, expensive, and sometimes even impossible.
So researchers are trying to find ways around that.
Yeah. They're exploring ways to train models without labels so they can learn from all this unlabeled data that's just out there waiting to be used.
So it's like teaching someone to ride a bike without holding onto the handlebars. You let them figure it out on their own.
That's a great analogy. Self-supervised learning could really open up a whole new world of possibilities for deep learning.
That's fascinating. What else should we be keeping an eye on?
Another exciting area is multimodal learning.
Okay.
This is where you train models that can handle information from multiple sources like text, images, audio.
So like giving them superpowers, letting them see, hear, read, and understand the world like we do.
Exactly. And this has huge implications for fields like robotics, where we want robots to be able to interact with the world in a more human-like way.
So we could have robots that can actually understand us.
It's definitely a possibility.
Wow, that's really cool. Anything else?
One of the most important areas of research right now is explainable AI. We talked about how deep learning models are often like black boxes, where we don't know how they make their decisions.
Right. It's like they're giving us the answer, but not showing their work.
Exactly. But explainability, it's crucial for building trust in AI, especially when it comes to things like healthcare, finance, and law.
Right. We need to know they're making decisions fairly, based on good logic.
And it's not just about trust. It's also about making AI better.
Oh.
By understanding how they work, we can fix errors, reduce bias, and make AI more reliable.
So explainable AI is like essential for making sure deep learning is used responsibly and ethically.
Absolutely. It's one of the biggest challenges, but also one of the most exciting areas of research.
Well, this has been an incredible journey into deep learning. We've covered so much ground, the basics, the applications, the challenges, everything.
And it's only going to get more exciting from here.
Absolutely. So join us for the final part of our deep learning deep dive, where we'll wrap up our exploration and delve into some of the big questions it raises about, like the nature of intelligence, consciousness, and the future of humanity itself. Welcome back for the final part of our deep learning deep dive. So we've gone deep into how neural networks work. We've seen some pretty amazing applications.
Yeah.
And we've even talked about some of the challenges, right?
Right.
But now, as we're kind of standing at the edge of this whole AI revolution,
Yeah.
I think a whole bunch of bigger questions start to come up. Questions about what it even means to be human.
It's true. As we're building these machines that can learn, reason, even create, it's hard not to wonder, where's the line between human intelligence and machine intelligence?
It's something I've been thinking about a lot during this whole deep dive.
Yeah.
On the one hand, we've got these incredible algorithms that can do all these amazing things, right?
Sure.
Diagnose diseases, translate languages, even write music.
It's crazy.
But at the same time, there's this feeling like human intelligence, it has something else, something more, something you can't just code.
It's a fascinating paradox, right? As these models get more sophisticated, they really challenge our ideas about consciousness, creativity, what it means to be intelligent. It makes you rethink our place in the universe.
Yeah, like, are we really the most intelligent beings, or are we just one type of intelligence on a spectrum?
It's a huge question, and I don't think we have all the answers yet.
Yeah.
But I think exploring these questions is like the most important thing we can do right now. It helps us understand intelligence better. Maybe there are other kinds of intelligence out there that we haven't even thought of.
This is all so exciting,
Yeah.
but also a little bit scary. It's exciting because it opens up all these possibilities,
Yeah.
but it's also kind of scary because it makes you question everything. Our identity, our control, even our place in a world with all these intelligent machines.
It's a natural reaction, I think. We're in uncharted territory here.
Right.
And it's totally normal to feel a little bit, overwhelmed by it all.
But I think this exploration, trying to understand intelligence, is going to be super important for the future.
Absolutely. It's a journey we need to take.
And we're not just along for the ride.
Right.
You can actually shape how AI develops. We can make sure it aligns with our values, with the kind of future we want.
That's so important. It's a responsibility for all of us. Scientists, policymakers, educators, everyone who's going to be impacted by this technology. We need to be careful about the data we feed these models,
Yeah.
the tasks we give them, how we integrate them into our lives.
That's like we're writing the next chapter in human evolution.
Yeah.
And AI is a big part of it.
Definitely.
But AI is a tool, right?
Mhm.
It can be used for good or bad. It's up to us to make sure it helps us, not the other way around.
I love that. We have this amazing chance to create a future where AI makes our lives better, helps us solve big problems,
Yeah.
and maybe even unlocks new human potential. But we have to be proactive. We need to have honest conversations about ethics and make sure AI is developed in a way that benefits everyone.
That's a message I think we can all get behind. This deep dive into deep learning, it's been an amazing journey. We've explored how it works, seen its potential, and asked some really big questions about our place in all of this.
It really has. And I hope our listeners are feeling inspired to learn more.
Me too. So thank you for joining us on this deep learning adventure. Keep exploring, keep asking questions, and keep imagining the possibilities.